Hi everyone, hope you're having a great day today. Today we're going to jump over to Sequence and Series, which is chapter 12, and we're going to cover chapter 12.1, 2, and 3. Now this chapter is super easy, so if you know how to add and multiply, this section should be a piece of cake. So I'm going to identify what is a sequence and show you how it is relating to functions. So a sequence is nothing more than a function where the domain is all whole numbers. So let's compare the two. So first of all, let's look at the notation. So the notation, we use f of x, g, or h of x in order to denote something that is a function. However, for a sequence, we're going to use a subscript n, or b subscript n, or c of n. Okay, and so our independent variable over here is x, and x can be any real number. Over here, our independent variable is n. However, n always starts at 1, 2, 3, 4, all the way to infinity. Now, some will use 0, but most of the time we will use 1. So therefore, we have the first term, and we use a of 1, a subscript 1. The second term, a of 2, a of 3 for third term, a of 4, and so forth, all the way up to a of n, where we call that the general term. Over here, we have the general term too, we just call f of x. Because here, we do not have first term or second term because our domain is all real number. Okay? All right. So what is the difference between a finite sequence and an infinite sequence? So a finite sequence basically just have finitely many numbers or elements inside of the set or the sequence, where infinite sequence go on forever. Okay, so here you see a finite sequence stops at n, and an infinite sequence go to infinity. So you can see here that they use the subscript an to denote f of n, which is the same thing. Again, if we try to graph something like this, let's see the similarity between the two. So for a function, let's say we have a line 2x plus 1. And for a sequence, we can write the same thing, except we use a subscript of n, 2n plus 1. So to graph this, we go to 1, which is our x, y-intercept, and then our slope is 2 over 1. So from our y-intercept, we go up 2 over 1, up 2 over 1, and so forth. And then we can connect these points to create a line. Okay, so for a sequence, it is very, very similar, except remember that n always starts at 1, 2, 3, and so forth. So that means that instead of a line, what we're going to have is just a point. So these points will fall in the same as these lines. So my first value, if I plug in 1 here, I'm going to have 3. If I plug in 2, I get 5. If I plug in 3, I get 7. So you see here, it's the same thing as over here, but for the function, we have a line. For a sequence, we have a bunch of points that fall in a line. Okay, so a sequence is always points, never lines. Okay, let's look at the first 5 terms of each sequence. All you have to do is plug in. So this is just like saying f of x is equals to x plus 1 over x plus 2. And I'm asking you to find f of 1, f of 2, f of 3, and so forth. This is exactly the same thing. All you gotta do is plug in the number, right? So here, the subscript is 1. That means that n is 1. So you plug in 1 whenever you see n. So you can see here, we are plugging in 1. So to evaluate that, just 1 plus 1 is 2, 1 plus 2 is 3. So 2/3, 4/5, 6, 7, and so forth. Okay. Same thing here. We're going to plug in 1 through 5 to find the first 5 terms. Now let's write this out. AN is equals to, the first one, A1, is -1. The second one is 2. Third one, -3, 4, -5, and so forth. Now this one's a little bit more interesting because you know that the first term is negative, second term is positive, third term is negative, and so forth. So here we have what's called an alternating sequence. So an alternating sequence alternates signs. Okay? But notice that the first term is negative. So basically all the odd terms are negative. But what happens if I want all the odd term to be positive? So let's write our formula for that. So if you look at the formula here, you notice that the -1 to the n is what makes it alternating sequence. So if you have -1 to the n, it's going to be negative, okay, when n is odd, and positive when n is even. Okay. All right. So what if I want the first term to be positive? So here, first term is negative. Now, if I want the first term to be positive, all I have to do is add 1 to my exponent. So here, we're going to have first term is positive. You can see why that is. Let's look. So let's say AN is equals to -1 to the n plus 1 times n. If I plug in 1, right, to find my first term, you have -1, 1 plus 1 is 2 times 1. So you can see here the -1, by adding 1, it makes it an even number for the first term. So here -1 squared is +1. 1 times 1 is just 1. Let's try 2. -1, 2 plus 1 times 2. This time is -1 to the third power. If it's to an odd power, it's actually negative. So we have -2, and so forth. So you can see here our first term is positive. And you can see here, -1 to the n, that makes our first term negative. And basically all the odd term number after that, all the odd term after that will give you a negative values. Okay. All right, convergent and divergent. So when we're talking about convergent of a sequence, we're talking about the value of those in the sequence get closer and closer to some real number. So we say converge to that number. So let's look at a graph to be able to understand this. So remember that the graph of a sequence is just a bunch of points. So here, if I draw a bunch of points, you can have an idea. All right, so you see here, this graph is converging to 0 because these term values, as it increases to infinity, it's getting closer and closer and closer to 0. So a sequence diverges if it goes to positive or negative infinity or oscillate. So we're going to look at examples of this later. Okay, so a sequence AN n squared. So let's look at with a graph of f of x equals to x squared. And by the way, these two are the same thing. AN is equals to n squared. So we know what the graph of x squared looks like, right? It's just a parabola. Now, if n or x goes to infinity, so as x approaches infinity, the y value also go to positive infinity. So you can see here, So therefore, this sequence will diverge because it's heading towards to infinity, not any particular number, but it actually goes to infinity. Well, it's the same thing for over here, except we're going to draw a bunch of points to represent that parabola. Okay, so still headed to infinity. Okay, next we'll talk about recursive formula. A recursive formula just means that we're going to use the previous term to find the next term. Okay, so let's look at some examples. And before we do that, let's look at some notations. So we know that AN means the general term. You can also think of it as the current term. And the notation AN minus 1, where we have the subscript, this is the previous term. And if we have AN minus 2, this is the previous two terms. Okay. So for example, if I have A1, A2, let's say this is equal to 1 and 2. So my next term is going to be A3. Now 3 is my current term. The previous term would be A2. The previous two term would be A1. Okay. So depending on what the formula looks like, you may need the one previous term or two previous term. Let's see what this example gives us. Okay, it asks us to find the first four terms of the sequence, and it already gives us the first term here. A1 is 4. All right, so now AN is equals to 2 times AN minus 1 plus 1. So let's interpret this here as 2 times the previous term plus 1. Okay, so we already know that A1 is 4. So to find A2, which is now our current term, we take 2 times the previous term, which is A1, plus 1. So the previous one is going to equals to 4. Okay, and then we plug into our formula. 2 times 4 plus 1 is 9. So now when we get to the next term, our current term now is A3. Our previous term is A2. Now, of course, you can also just plug n in here. So for example, if I want to do A3, I can plug in n to here, 3 minus 1 plus 1. And you can see here, this is asking you for A2. And you can plug in A2 there. Okay, but it's easier to understand in the term of English as you interpret it out. When you see n minus 1, it means the previous term. Okay. All right, so we use our previous numbers that we found, plug it in here for A2, and we get 19. And similarly, we take that number, plug into here. So the thing about recursive formula is that you have to find out the previous number in order to find your current value. So let's say I want to find out what is A10 is equal to. Well, I can't do that with a recursion formula because I have to find A9. If I want to find A9, I have to find A8. And if I don't find A8, I have to find A7 and so forth, right? So there is benefit to using a recursion formula. We use this a lot in computer science in order to generate codes, basically to go down like something like a factor tree. We call this a decision tree. So this is a quick crash course of computer science if you're interested in that. So a recursive formula basically allows us to follow the possibilities of every single branches. So what it does is that it follows the most obvious one, so the most straightforward path. And then that doesn't work, it backtrack and then goes to the next path. And then that doesn't work, it goes backtrack, it goes to the next path, and so forth. Okay, so this is what recursion are used for in computer science, not for formulas like this. Okay. Okay, find the first 4 term of the sequence. All right, so here we use the previous term and the term number itself. Okay, so here they give us the first one is A2. Now we need to find out 3 more. So A2 is my current term, A1 is my previous term, and since I know what A1 is, I'm just plugging it in. So 2 plus 1 is 3. Then we take that and plug into the next one. Next term is 3, plug it in, 3 plus 2, because we actually simplify this. Our term number is 3, so that's the n value, minus 1, give us 2, 3 plus 2 is 5. So after you do a couple of them, you can see a pattern here, okay? So here, 3 to 5 is plus 2, 5 to 8 plus 3. Now, maybe I'm guessing the next one may be plus 4. However, with a recursion formula, you can't always be sure. But let's try and see. So let me say A4 plus 5 minus 1. So A4 here is 8 plus 4 equals 12. 8 plus 4 is 12. So that's the pattern here. So a lot of times you may need to go to 3 or 4 terms to identify what the pattern is. So don't always jump straight to it when you only have, only 2 values so far. Okay, so we're modeling insect population growth here. So the winter moth population in 1,000 per acre in years, N is modeled by AN 2.85 of the previous one minus 0.198 square of the previous one. Give a table of value for N from 1 to 10. All right. And graph the sequence, describe what is happening to the population density of the winter moth. Okay. So we can definitely do this. Now you can also do this in a graph using graphing calculator as well. So this is N, AN. So 1, 2, 3, 4, all the way down to 10. So the first one is given. It's 1. 2, let's plug the values in here. And we're using the previous values for this. So we're going to plug in 2.85 times 1 minus 0.191 square. So this 1 I got from the previous term, right? Because AN minus 1 is the previous term. So let's find out what that is. Well, instead of typing that in, let's see what we got over here. We got 2.66. Let's just follow this here. All right, so the first term is 1, the second term is 2.66, and so forth. Okay, so here is our first 10 values, and you can see here we have 1, 2, 6, 10, and so forth. Okay, so what's happening here? You can see that it's oscillating between these values here. So this looks like 9.7 fluctuate around these values. Now, the reason why that is, this is actually a real world application here, is what's called a carrying capacity. So let me explain why we have a graph like this. Okay, so this is talking about insect density in 1,000 per acres. Okay. So what's going on in real life is that when you have a certain area, so let's say this is 1 square acre. So of course that's going to be food and that's going to be predator. So in a certain limited space, that means that the insect can only eat a certain amount of food that is available because it's finitely many food, right? So you can't eat infinitely many food. So you can only multiply so quick depending on the natural resources that you have. There's also predators, so that means that you can only grow up to a certain size, and then the predator will eat the insect, which keeps the population down. So why is there a fluctuation like this? The fluctuation comes from new insect being born, and the natural resources enable it to multiply. So when there is a population boom, for example, you may go above this carrying capacity. Now I'll explain what carrying capacity is in a second. And then maybe due to food or predators, the population will decrease. And then as time continue, it's going to give birth more, and then the resources come back and so forth, and it's going to fluctuate back and forth like this until it gets to 9.7 thousand. So what does that number mean? So that value is called the carrying capacity. Carrying capacity is the amount of life it can sustain in a limited area or space. Okay, so within a limited amount of area or space, you have a limited number of food and natural resources. So therefore, you cannot grow beyond that. Okay, so for example, let's think about if we have, an island, and we have a bunch of rabbits on that island. So of course they will multiply. If well, let's just talk about food. Don't talk about predators. So let's say that let's say there's only, I don't know, 10 rabbits on this island, and there's a bunch of grass or whatever rabbit eats for it to eat, right? So it's going to have all the time in the world to multiply. Now it's going to multiply until it becomes too large, which means that there's not going to be enough food on this island to sustain that number of rabbits. So that means the rabbit is going to go hungry and it's going to die off. Well, when they die off, there's going to be a large amount of them that's going to die off. So basically you have that boom of population where there's a lot of food and then you eat it all, but you eat all the food that the grass is not able to grow fast enough to sustain that population, so they all die off. So when they die off, they die off a large amount of time, and then after they get below here, that's going to give time for the grass to grow, and then the population is going to boom again. So therefore, it's going to repeat the same process, but each time they do that, the amount is getting smaller and smaller. So the amount of boom that they're growing and dying off is smaller until they met the carrying capacity, which means at this point, the number of rabbits is equals to the amount of food that is naturally grown for it to survive. So therefore, there's that balance in life, right? So if you have enough resources and for a limiting number of people or living things, then you can sustain that forever. So if we use that for, I don't know, the world population, then we're in trouble because we have limited water, we have limited natural resources as oil and oxygen. So therefore, we cannot continue to grow at the rate that we're growing right now. If you look at the world population 70 years ago, we almost doubled the world population. So yeah. Okay, so now let's look at series and summation notation. A series is nothing more than the sum of the first finitely many values. So let's look at what it means. So S1 means the sum of the first term. because the 1 here denote how many terms of a sequence you're going to add up. So S2 means sum of the first 2 terms. That means A1 plus A2. So S3 means A1 plus A2 plus A3. So there's 3 terms. This is the subscript here. All right. So Sn is equal to, this is sigma. It's a capital sigma. It means summation. So I equals 1. The value down here is called the index. Now, sometimes we use I, sometimes we use J, and sometimes we use K. I and K are used the most, sometimes J. And then the end value here is the ending term. So this is called the first term, starting term, I guess. Okay, and the value in here is the general term. That's like the formula that we saw earlier. Okay, all right, let's look at some examples. So you go over finite series means that you add finitely many numbers. Notice that a finite series always starts with 1. Okay, so note a series always start at 1. Okay, if you have something like this where I starts at 10 and then it ends at 20, this is just called a summation, not a series. And an infinite series is denoted by S with a subscript of infinity, or sometimes we just drop that and we just call it S. Now this gives us some interesting aspect later on. I'm going to show you what it means by that. Okay, so find the sum of the series. So let's see, we have summation from k equals 1 to 6 to k plus 1. So notice that whatever your index is, you have to use the same variable here. Because if you have k here, and let's say you have I here, then this I is now a constant. It is not an index. Okay, so be careful that they must match. Okay, so since this starts at 1, this means that this is the sum of the 6 terms. So now we have a series. So this is the general term. So we're going to plug the index in here, starting at 1. So that means we need A1, 2 to the 1 plus 1. Okay, A2, 2 squared plus 1, and so forth, to A6, 2 to the 6 plus 1. Okay, so here we have all of our 6 value added together. And so that's what the summation of 6 means. We're going to take 3 plus 5 plus 9 and so forth, and we add all 6 of them together to get 132. Okay, so write the term for each series, which is expanding here. Notice that this is not really a series because it doesn't start at 1. We just call this a summation. So this is our starting point. So A3, A4, A5, A6. Notice that here, since we start at 3 and we end at 6, we do not have 6 terms, right? So in order to find out how many terms there are, you take the ending number, subtract the starting number, plus 1. So here I started at 6. I'm ending at 3. So that gives me 3 plus 1 is equal to 4. So you see here, we have 4 terms total. Okay. All right, let's try this one. So here we're starting at 1. going to 3, so we're going to have a total of 3. So we're going to plug in I. And you notice here x is a variable, but here we're going to treat it like a constant. The variable in here is I. I is the one that's changing. So as you move from one term to the next, that's the value that you're changing. So A1 means we're going to plug in 6x subscript 1 minus 2. A2, 6x2 minus 2, and so forth. Oh, actually, that's just 3, right? 6x to the third minus 2. Then we can add all these together. Okay. Now here they give us what x1, x2, and x3 is equal to. So we can do a direct substitution in here and end up with 66. Okay, so here's where the fun stuff is. When you get to calculus, this is what you will start seeing. And when people start seeing this, they freak out because there's triangles and subscripts and there's F and all this stuff. This might look very confusing at first, but let me break this down for you. First of all, let's inspect what this summation is. Okay. Now, when you get to calculus, you're going to understand what delta x means. Oh, by the way, this is a delta. This is a Greek letter, D. Okay, capital D. So for pre-calc, don't worry so much what this delta x mean. Just know that it is a constant. Okay, so right now we don't care what it is because it's not going to be affected because there's no I in here. So the only thing that has an I in here is this here that we need to evaluate with. So what we can do is, since that it is not a variable of this sequence, we can actually take it outside. And we write this as delta x times this. Okay. Then we can evaluate just this portion right here, leaving this delta x outside. So now let's plug in I equals 1. We have f of x1 plus f of x2, and we go all the way up to 4. Okay, now let's see if they're going to give us the value for it. Here they tell us that f of x is equals to x squared. So now you can do a direct substitution by plugging in here. Now, what is the value of x1, x2? So here they give that to us right here. Okay, and delta x was 2. All right, so now we can evaluate. So we know that delta x is 2. Now, x1, x2, x3, x4, they also give us that that's 0, 2, 4, and 6. Okay, now we can evaluate using this because f of x is defined as x squared. So now I'm going to take this x and plug it into x squared. So 0x squared, 2 squared, 4 squared, 6 squared. Okay, so this gives me 0, 4, 16, 36. So this gives me 40, 56 times 2 be 112. Okay, so that's what they got here. Now you see here what they did is they did not factor out delta x. Okay, that just seems more work. So just remember, if it does not have an index in it, whatever index that is, could be I, J, or K, you can always factor it out to the front. Okay. You can only do that if it's multiply or divide. You cannot do that if it's addition or subtraction. Okay. You have to break up the whole summation for you to be able to do that. But we'll look at some examples and properties of summations. Okay, let's talk about an infinite series. Okay, so we have this infinite series to approximate pi. So we're going to approximate pi by finding the sum of the first 4 terms. And then we're going to use a calculator to approximate pi by summing the first 50 terms. All right, so let's look at the sum of the first 4 terms. So let's see if you can recognize the pattern here. Notice that all the numerator is 1. And the denominator, so the easy way to determine what this is look at the term number. The term number here is 1, 2, 3, 4, 5, and you know that they are using the term number, and all of these is to the 4th power. So our general term is 1 over n to the 4th, which they give it here. Sometimes they give you this, sometimes they don't. You have to figure this out yourself. All right, so let's find the sum of the first 4 terms by just plugging in here. All right, so we have 1.078. Okay, so we're trying to estimate pi. We know pi is about 3.14, right? Now, if I do this right here, I have 1.0787. Then we're going to solve for this by multiplying by 90. And then taking the 4th root of this. So we have 3.139. So you can already see, using only 4 values, I got pretty close, 3.14. So this 9 right here, we're going to round this up. So it's a pretty good approximation of pi after only 4 iterations. Now, if we need more, of course, a computer can calculate this for us much faster. Doing it the first 50 terms, you can, of course, plug this in here. Now, if you don't know how to do this using a calculator, I will show you. So let's move to our calculator. Okay, so here we need to pull up the sequence. Now, if you have an updated calculator, it would be here. If you type alpha window. So you see the summation right here in the second choice, press 2, and then it will show up here. Now you need to find out what is your index. Now you can choose whatever letters you want, I, J, K, A, B, C. It doesn't really matter here as long as when you type in the general term, it's the same thing. So here I'm just going to use X because X is the button right there. I don't have to go to alpha and choose whatever, but you can do that. I'll show you here. Hit alpha, and then you can choose any of these letters you want. So since the book used K, I'll use K here. Starting at 1. And now we need to go to 50 terms. Now you have to use K again because that is your index. K divided by, 1 divided by K raised to the 4th power. There you go. And give us 1.0823. Now remember, we want to multiply this with 90. So we press second answer. So I was going to use this answer right here for the calculation, times 90, raised to the, we need to take the 4th root of this, and the 4th root is the same thing as 1/4. And we got 3.141590776. So that's pretty good. Now let's see what is the exact value of pi. Pi is actually stored in here for you. So let's see. And we're good up to 5 decimal places. So even though we went to the first 50 terms, that does not get us any much more accurate than what we did with 4 terms. With 4 terms, we were able to get to 2 decimal places of accuracy after you round. Okay. Okay. Okay, so now we talk about summation properties. This will help you evaluate summation much easier, unlike the 2 previous examples that we did. Okay, so if you have a summation, the C value here is a constant. So if you have just a constant, then you can evaluate this summation by just multiplying by how many terms there are, and here you have n terms. Now again, this is very important. You have to start at 1 for this to work. If this does not start at 1, you cannot use this property. Okay, so let's think about it. Let's look at an example. And if I have a constant 3 here, now notice that I do not have an index for me to plug in, right? So each time I'm adding the same number, 3 plus 3 plus 3 plus 3, 4 times, right? So another way I can do this, right, is do 3 times 4, or n times c. Now, since this is also a constant, I can factor it out. So if you factor it out, you just have this. So nothing to plug in here. So you have 3, 1 plus 1 plus 1 plus 1, 4 times. So 4 times 3 is still the same thing, right? And so here I show you that if you have C and some other terms, you can factor out C outside. And that's what I showed you before. Now I told you that you cannot take out when you have addition or subtraction. You have to actually break it up into 2 different summation. Okay, so here you have addition here. Now if this was a constant, you can do the same thing. Okay. All right, so anytime you have addition, you can just break it up by breaking each of the summation into each term. So this is 1 term, this is 2 term. So you can break it up into 2 summation with exactly the same values for the starting and the ending. Okay. And here is something you should memorize to help you evaluate summation. So here, the first one is somewhat obvious. You kind of learned this in college algebra. And I can show you how to derive this, but for time's sake, we can just memorize this formula. And so if you have I, and I here is whatever the index is. So here, this is just like 1 plus 2 plus 3 plus 4 plus 5, all the way up to n. So the formula for that is n times n plus 1 divided by 2. So write this in your note card. For I squared, it's a little bit more elaborate. N times n plus 1, and then you have this extra piece here, 2n plus 1 over 6. For I cubed, you have n squared times n plus 1 squared over 4. So we can use these properties in order to evaluate this much quicker. So here you have just a constant. You have 40 here, so all you have to do is just take the constant times n, so c times n. My c here is 5, my n here is 40, so you get 200. And then the 2 here, you can factor out the 2, just that they did here, and then you evaluate by using the rule over here. If you have I from 1 to n of just I by itself, then you can just plug in the value for n here. So my n value is 22. I factor out n here. So this is n times n plus 1. Okay, so plugging in, you get 5 over 6. For the third one, now we have to break this up. So here, because we have subtraction, we need to break this up into 2 summation. All right, and then we have to take this 2 out. so that we just have the I squared by itself. And this is just a constant, so that one's easy. You just leave it like that. And now we can evaluate this piece right here. So we have a formula for the I square. You can see here, n times n plus 1 times 2n plus 1. Well, what is n in this example? Well, n is your ending number. So we're going to take 2 times n is 14 times 14 plus 1. 2 times 14 plus 1 over 6. So all this is just the first term. Minus, this is just a constant, so we have 3 times 14. And doing all that give us 1988. All right, for this one a little bit more involved, but it's still the same thing. You have an I square, you have an I, and you have a constant. You break it up into 3 summations, and then you take out all of the constants, like here's a constant right here. And since there's no variable in here, we can just leave it like this because it's just n times c. Over here, we're just using the formula where n is 6. So it's just applying the formula that we have over here. Okay. And we end up with 184. Okay. Okay, so this section is fairly easy. All you have to do is memorize these formula here, and I think that's the main formula. Oh, this is just notations. It's just a very straightforward section. Okay. All right, so we're gonna start on 12.2 next week, and we'll finish up at 12.3. Before we hit Thanksgiving. After Thanksgiving, we're just going to review everything for exam 4 and the final. Okay. All right. Hope you have a great week. I'll see you next week. Bye.